The next thing I want to talk about is graphing radical functions. So let's look at y equals the square root of x minus 1. Now, some things we're going to want to do, and I talked through this in class, and I believe in a previous PowerPoint video, is that you want to set your radicand, so it's under the radical, equal to the first few perfect squares. So the first few perfect squares are 0, because 0 squared equals 0. The next perfect square is 1, because 1 squared is 1, followed by 4, because 2 squared is 4. So let's go ahead and solve these. I meant for this to be a 5, y'all, but I'll show you why in a moment. So I'm going to add 1 to both sides. So that means x equals 1. I'm going to add 1 to both sides, so x equals 2. And I'm going to add 1 to both sides, so x equals 5. So these are our values we're going to choose because they make our radical really nice square roots. Since we're taking a square root, that is crucial. So let's plug it in and see what happens. So if I take the square root of 1 minus 1, that's the square root of 0, which is 0. If I take the square root of 2 minus 1, that's the square root of 1, which is 1. If I take the square root of 5 minus 1, that's the square root of 4, which is 2. The reason I chose these x values is so that I could get nice rational numbers in order to make it more easy to graph. It's really hard to graph things like the square root of 6. Where is that? You could punch it into your calculator and get an approximation, but this makes life a whole lot easier. So let's go ahead and graph this. I'm going to have when x is 1, y is 0. When x is 2, y is 1. And when x is 5, y is 2. So here's our radical. It's our radical shifted 1 to the right. Okay, so even though we were subtracting 1, it went 1 in the positive direction, so 1 to the right. We saw this when we were working with quadratics, that if I have something taken directly away from the x, right, kind of in parentheses, because we could rewrite this radical as an exponent of 1/2, if I'm subtracting, it goes 1 to the right, and if I was adding, it would go to the left. So why don't we practice graphing a few of these after I talk about domain. So remember, our domain is all possible x values. So my possible x values go from when x is 0 to positive infinity. And 0 is included, so square brackets. And my range goes from when y is 0, all the way to positive infinity. Isn't that so exciting? So from 0 to positive infinity. I made a mistake. Does anybody see what it is? My domain starts when x is a positive 1, not when x is a 0. So we need to fix that and write when x is negative 1. All right, always good to double check yourself. Now let's take a look if I have negative square root of x minus 2. When we were working with quadratics, if I had a negative out front, what did it do to my graph? Okay, it flipped it. It made it upside down. So let's see what's going to happen with my radical function here. So I take my radicand and I set it equal to the first few perfect squares, which are 0, 1, and 4. So I have x equals 5, x equals 2, and x equals 1, just as in the previous slide. When I plug in my value, I have negative the square root of 1 minus 1, which is negative the square root of 0, which is just 0. Negative the square root of 2 minus 1 equals negative the square root of 1, which is negative 1. Negative the square root of 5 minus 1 is negative square root of 4, which is negative 2. So let's go ahead and plot this. I have when x is positive 1, When x is positive 1, y is 0. When x is 2, y is negative 1. And when x is 5, y is negative 2. My original graph was up here, right? My original graph, we're going to draw it right here. My original graph kind of looked like this. So you can see from the previous slide. So what it did when I take a negative out front is it reflects my graph across the x-axis. It reflects it as if you stuck a mirror right here. That's what you'd see, a reflection. Okay? My domain goes from negative 1 to positive infinity. I mean positive 1 to positive infinity. And my range is now from 0 to negative infinity because I flipped across that y-axis. Okay? So when there's a negative out front, it is going to flip our graph. Now, what if I have y equals 2 square root of x minus 1? Now, I'm going to be multiplying by a constant. Let's see what happens. I know from the last 2 slides to set our radicand equal to some perfect squares, which are 0, 1, and 4. And I got 1, 2, 5. So now I'm going to take 2 times the square root of 1 minus 1, which is just going to be 2 square root of 0, so 0. I'm going to have 2 times the square root of 2 minus 1, which would give me, it's an equal sign, 2 times the square root of 1, which is 2. I've got 2 square root of 5 minus 1, which is 2 times the square root of 4, which is 2 times 2, which is 4. Okay, so let's go ahead and plot this. I have when x is 0, when x is 1, y is 0. When x is 2, y is 2. And when x is 5, y is 4. Nope, down here, 4. All right. Let's go ahead and connect these points. Now, how does this compare to our original graph from the first slide of y equals square root of x minus 1? It looks like my graph has kind of been stretched upward, okay? When we multiply by a constant, we'll call it a, greater than 1, greater than or equal to 1, that's going to be when we have a vertical stretch, right? It stretches my graph up vertically. It's going to have the same domain and range as the original function. My domain is from 1 to infinity. My range is from 0 to infinity. But my graph has just been kind of stretched upward. Now, there's another thing we have, not vertical stretch, but if something's not being stretched, it's being shrunk. So let's take a look at y equals 1/2 square root of x minus 1. I know my x values are going to be 1, 2, and 5 from the previous couple of slides. So I have 1/2 square root of 1 minus 1, so 1/2 square root of 0, so 0. 1/2 square root of 2 minus 1, so 1/2 the square root of 1, 1/2. Then I have 1/2 the square root of 5 minus 1, which is 1/2 the square root of 4, so 1/2 times 2, which is 1. Okay, so let's go ahead and plot this. I have when x is 1, y is 0. When x is 2, y is 1/2. And when x is 5, y is 1. So here's our new graph. Let's take a look at how that compares to our old graph. It looks like my graph has been kind of pushed downward. We call this, when we're multiplying by a constant that's less than 1, we call this a vertical shrink. It's pushed my graph down. The domain has remained the same, though, as our previous page where we were looking at a vertical stretch, and as our original function, the domain goes from 1 to infinity, and the range goes from 0 to infinity. So it's important to note with vertical stretches and vertical shrinks, the domain and range do not change.